everyone, so now we're going to learn how to write a DriveWithMotionProfile drivetrain command, and this is going to be a generic template so that we can pass any paths we want into it, and it will start our profile for us. And remember, we're going to be generating it with a different application this season, or this off season. We're going to be using the one from GitHub for the Deep Space game. So this command you'll be able to use for any game regardless. You just pass in whichever paths you want to pass into your drivetrain talons, and it will run it for you. So it's pretty simple to understand. Don't worry if it's complicated or it's hard to understand. Just take your time. You can rewatch videos, ask us questions, whatever. So first I'm going to go to the CTRE API for Java, and it basically is a super helpful website that contains all the classes from CTRE, which creates a lot of the things we use on our robot, such as the talons and sensors that we use. So I'm going to set up my class really quick, just the typical Java stuff. You can skip ahead. Remember, it extends command because it is a command. And every time I ask a question, you guys can pause, think about it, or if you get it really quickly, you don't need to pause. Just try to think about it on your own before you hear the answer. So I'm going to make the constructor. And what is the most important statement that we always put first in our constructor of a command that requires? So we're going to be requiring the drivetrain because this is a drivetrain command. And I'm going to import and add an implemented methods. Okay, great. So I'm going to explain what a trajectory point is. So by now you probably should have done your 2 double arrays that you generated, and each array inside is going to represent a point. Remember, motion profiling is like motion magic. You generate lots of points, usually in the hundreds, and each point the talon is going to be going to, or I guess your robot, because you're going to be feeding points into each talon that tells the robot where to go and how, with your position, velocity, acceleration, with each point. So basically all we're doing is going to be setting up trajectory point streams containing all your trajectory points, and this is basically just going to be converting your 2 double arrays for each side of the drivetrain into trajectory point streams that the talon can then read and motion profile to. So the trajectory point stream basically represents one array of one side of the drivetrain, and each trajectory point is going to be every array of position, velocity, and acceleration inside. So we can go to our CTRE and we can look at the buffer trajectory point stream, which is what it's called. And you can see here that there's a method, right, that is overloaded. So you can either pass in trajectory points, an array of trajectory points, based on how you want to implement creating your trajectory point stream. So yeah, let's create 2 instance variables of buffered trajectory point streams, one for each side of your drivetrain. Okay, and then since this is going to be used, this whole command is going to be used for whatever paths you make, we're going to pass in our left path and right path, the double ones, as parameters. That way it can be very flexible for which path we're passing in. And because we're only going to be making the streams inside our constructor, we don't need to do it in initialize or execute, because we don't need to recreate the same streams every time you click a button or whatever to initialize, because it's going to be the same one throughout. The same one you pass in is going to be the same one you run throughout. So you don't need to recreate the entire stream and initialize every time. Doing it once in the constructor is enough. So now we've defined these two buffer trajectory point streams, and we're going to have to instantiate them or initialize them inside our constructor. Actually, I'm pretty sure it's instantiate because we're creating objects with the keyword new. So yeah, we can create them. So now they're both empty trajectory point streams, and we need to fill them up. So I'm going to create a helper method. You can do it inside the constructor directly if you want, but since it's going to basically be the exact same thing with a few minor differences for setting up your left path and your right path, I'm going to make a helper method just to clarify, not clutter up the constructor, and make it easier to implement. But in the end, it's up to you what you want to do. So we're going to take in the buffer trajectory stream that we want to add in points to. We're also going to take in the path that we're going to convert into the stream. And we're going to specify whether it's the left or right stream, because later on when we do gravity feed forward or any characterization things, we might need to change constants based on whether the point is on the left or the right side of the robot. So that's why we need this Boolean. And we're gonna, if you want, you can pause the video, try to do it on your own. But first, I want to show you guys the trajectory point API. So these are all public attributes. Once you can, or a major hint I'm going to tell you is to create your trajectory point with the noargs constructor, and then just alter the public attributes directly. So once you've created your trajectory point, you can set like position, velocity, arbitrary feed forward, etc. Otherwise, if you use the constructor that takes in all of these, there's a lot that we probably don't need to set up, and the default is already good enough. You guys can pause, try to do it on your own with like for loops or whatever Java knowledge you have if you have any ideas on trying to create a trajectory stream. And then just remember to use the method right to then put in your trajectory point into the stream. If you have no ideas, or if you finished and you're going to resume, I'm going to help you implement it. So we're going to make a for loop, just a generic one that's the size of the path length. So the path length is going to be the total number of points in the path, and this is going to be the same for the left and right side. So we're going to create a new trajectory point. And then we're going to set up position, velocity. We're going to put in an arbitrary feed forward, but we won't calculate it. We'll just set it to 0 for now until we start tuning. We don't need heading degree. We don't need aux position, aux velocity, or aux arbitrary feed forward. We're going to select the profile slot as 0, the 0 profile slot. We're going to set that to our motion profiling slot. And then we're also going to implement isLastPoint, the 0 position. And we don't need the time duration because we're going to be using a time duration that's part of the motion profile trajectory period, and we don't need to worry about time duration for now. If you're confused about it, you can ask me or Jayden later. And we're not using auxiliary PID. We're just using one motion profile PID as our primary. So we can set up the simple ones, position, and we're going to have to convert from feet, which our motion generator gives us the position in, into encoder units that our talons can then read. So yeah, we're going to convert. And as you can see, the first parameter is a start unit, that's feet, and we're going to use an enum from Harker Robolib. We're going to pass in the value, so and this is specifying in this specific point of the trajectory or of the path, the first argument of that array, which is position. If you remember P, V, A, and H, which H we're not using. That's just the header. And then we're converting it to position unit dot encoder units. That way our talon can understand that the value is in the right unit. Next we're going to do velocity. Our velocity in the double array is given in feet per second, and we want to convert it to encoder units, speed unit encoder units. So again, we're going to convert. It's basically like encoder units per 100 milliseconds, but encoder units are very weird units, and they don't really work like that. So for now, we'll just call it encoder units in terms of speed. So we have another helpful enum, and we're starting out as feet per second. This argument is going to be the one after position, so that's 1. And we're going to be, our desired unit is, speed unit, encoder units. Okay, let me import. Okay, and then now we're going to do the same for acceleration. Or sorry, we don't do acceleration like this. Acceleration is part, it's going to be used to calculate our arbitrary feed forward. Sorry, I think before I said gravity feed forward. We don't need that. That's for elevators and things that are going to be going against gravity. I meant to say arbitrary feed forward. When we characterize our drivetrain, which is, if we haven't reviewed this, characterizing the drivetrain is just creating an open loop so it doesn't depend on error like PID does. It's just going to rely on acceleration, static friction constant, and velocity constant, KF. So yeah, but for now, we're not going to be implementing acceleration and all those constants for arbitrary feed forward. We're just going to set arbitrary feed forward to 0, or if you want, you can comment it out since we're not really using it now, but its default is 0 anyway, so it doesn't really matter which one you do. Just keep arbitrary feed forward in mind. So after position velocity, arbitrary feed forward, we're going to do 0 position. So if I equals 0, then the point is the 0 position because we always start at 0 and equals true because it is a Boolean. Next, we want to implement is last point. So remember the path length is always 1 plus the last element. So equals true. That should be it for that Boolean. Next, we're going to set the profile slot. So we're going to have a set of motion profile constants that will work regardless of the path you choose. and each point will have its own slot for those motion profiling PID constants. So we have to set that up. So I already have a motion profile slot. You can make that in your DriveChain class, make it a static constant, like your other slots. And that should be it for profile slots. And now we finished creating our trajectory point. So we're going to write that into the stream that we've passed in. So stream.write trajectory point, and that is point. If you want, you could create a whole array of these and pass in the whole array, but personally I think that's kind of redundant because you could just write in the point at the end rather than add it to another array and then pass in that whole array. So yeah, that should be it for the setup trajectory stream for now. We might have to go in and do extra stuff later depending on our arbitrary feed forward. So now we've created the helper method. We want to set up the trajectory point. Oh, we should call it setup stream, sorry, because essentially that is what we're doing. We're setting up the trajectory point to set up the stream. So we can call setup stream left stream. And by no means do you have to copy all the naming convention or names I'm using. You can, if any make more sense to you, please use that. So for the left stream, it's going to be left is true. Otherwise, for the right, it's going to be false. Okay. So now we've set up the streams. We want to configure the motion profile period because, again, this is Talon side motion profiling. You could do Rio side. That's kind of more complicated and less intuitive. So we'll just be sticking to Talon side. So, sorry. We need to get it from the DriveChain. If you're familiar with lambdas, you could use the HS DriveChain apply to masters method with lambdas. If not, it's easy. We can just add one extra line and get the left master and right master that way. We'll be configuring motion profile trajectory period. So yeah, you can read this little description. Basically, the time duration that we're passing in is how long to apply the active trajectory point. So yeah, we can do a time duration. And the time duration will be different for each path. So we can pass that in as another parameter. Oh, I don't think it finished. There we go. Oh, it has to be an int. I think it's because it's in milliseconds. And now we're going to do the same thing for the right master. And these should be the same time because it would be weird if one of your points took longer to generate than the other side. That would mess everything up. Yeah, so that should be good for the constructor. So now in initialize, we're going to want to start the motion profile. So we can add that in. And the @override tag is just a helpful Java doc trick. Sorry, I was copying from isFinish. It's actually void that basically tells you that this method is being inherited from your superclass. So in case you spell it wrong, which can be really common, you don't know why you're having an error, the @over tag will help you quickly debug that. So it's always good to have. So now we're going to, so in here we've set the profile slot to the motion profile slot, but when we're actually going to run the motion profile, remember we need to bind that profile slot to the actual index. That will be the primary index that will be run. So we're going to do that for both the left and the right masters. And again, if you're familiar with lambdas, you can use the apply to masters method. But for now, we'll just get each like this. And select profile slot, slot index, the motion profile slot, PID index, or sorry, I think this is robot map since it's applicable not only for the drivetrain. Yeah, so we're going to bind it to the primary PID index and do the same thing for the right master. Great, so now we're going to start the motion profile on each side. Yeah, so to start the motion profile, we'll need the stream. The minimum buffered points is basically the minimum amount of points it has to kind of take in, because the stream won't be coming in all at once. But once you get the minimum buffered points that the Talon will take in, it can start the motion profile. That way we don't have to wait a really long time for all the points to get loaded in before we start the motion profile. Once we have that minimum amount of points, we can just go, and then as we're going, more points will be loaded in. So we can make a constant for that. Or if you want, you can make it a parameter in case you want to change this minimum. But for now, I'm going to make it a constant. Maybe 4. And control mode dot motion profile. Hopefully that makes sense because we are motion profiling. And we're going to do the exact same thing for the right master. Okay. So that should be it for initialize. So we'll start up the motion profile. We don't need anything in execute. If you want, you can make this an instant command since we're putting nothing in execute. However, when we're tuning our motion magic motion profile, we definitely do want print statements in our execute, which is why I'm going to leave it as a command for now, because it will definitely be filling up with smart dash statements to print error. And then in is finished, we want to return when we finished. So we're going to have to see if both the left master's path has finished and the right master's path. We don't want to end it if only one has finished or neither. That doesn't really make sense. Yeah, is motion profile finished? Okay, that should be good for is finished, and that should be it. Thanks for listening, and I hope you understand it. If you have any questions, This stuff is pretty complicated, so don't worry if you have questions. Just talk to me or Jayton, and don't be afraid to ask at all. This stuff can be very difficult.